Okay. Yeah.
Okay, maybe we can start.
Yeah, you have the floor.
Okay. Thank you, Dr. Longla, for the introduction, and thank you, Professor Zhang, for the invitation. It's really my great pleasure to share some recent work on the dependence measures. So this work is mostly about the probabilistic relations between two correlation coefficients, namely the Spearman and the Chatterjee. The Spearman's correlation is very popular. Everybody knows that. And the Chatterjee's correlation is relatively new, which I think first came out in 2019, and is a very useful and a pretty innovative correlation metrics. And my motivation to study these two particular correlation metrics is, to me, they are both similar and complementary. Similar in the sense that they are both rank-based and asymptotic normal, and complementary in the sense that Spearman is good at detecting monotonic association, and the Chatterjee is good at detecting non-monotonic association, just like oscillating patterns. And the natural question here is whether we can combine these two, because they are kind of similar and complementary, into a new test or kind of a versatile test that can be used to detect both monotonic and non-monotonic association with satisfactory powers. Of course, the first step will be some study on the relations between these two correlation metrics. That's the motivation. That's where this work comes from. And this is how I outline this talk. In the first part, I will talk about some brief, just a brief review for the Chatterjee's correlation and introduce some related literature. In the second part, we'll dive into some details of this work. We will show under independence, these two sample-based correlations are joint normal and joint independent asymptotically. And then in the last part, we'll combine these two tests into a new one, and then I will present some result by simulation data and also the real data. The real data is just from the transchromotomics, which is the yeast gene expression data. Let's start from the first part, which is the setup and introduction. Some basic setup. Suppose we have two continuous variables, x and y, and a bunch of IID samples from xy, and you can use x1, y1 to xn, yn. And we are interested in the classical independent test. The null hypothesis will be independence between the two variables, and alternative hypothesis will be the dependence between the two variables. And I think the two most popular correlation tests will be the Pearson and the Spearman, but we know the limitations of them. For example, Pearson's correlation can be only detect the linear relations, and the Spearman correlation can be only used to detect the monotonic association. So what if the relation underlying is not monotonic, is a non-monotonic, for example, oscillating patterns? We need some so-called consistent test, which means it can be used to detect any form of association. And here I list some existing method. For example, the distance correlation, sign covariance by Bergsma and Dasius, copula-based correlation, and the kernel-based correlation, among many others. For example, the kernel-based correlation can be the so-called HSIC. And for all this mentioned tests, in terms of the validity, they're all good. They can be used to detect any form of association, including the non-monotonic association. But the common and major bottleneck is the testing process. For most of them, there's a lack of simple asymptotic theory, which means you cannot simply use very like analytical calculation to get the p-value. Instead, oftentimes we rely on some expensive permutation test, which is very time-consuming. For example, for the distance correlation is very popular, but the problem is that the null distribution of this correlation matrix is in general not derivable. Okay? And actually, there's some paper on that. So the null distribution is actually in the form of weighted chi-squared. And we know the weight actually depends on the distribution, depends on some eigenvalues. And if you do permutation test, the time complexity is in the order of r times n squared. And r is the number of permutations, and n is the sample size. Okay, so when you have a large sample size, the permutation for distance correlation can be very slow. And that's the problem. And one exception is, the Chatterjee correlation. In 2022, actually, the preprint came out in 2019, and the paper is published in 2021 in JASA. So this paper introduced a rank-based correlation test. It's also consistent against all alternatives, just like the aforementioned correlation test, but asymptotic, normal, and independence. And this will make Chatterjee correlation stand out from the others, okay? Because for all the others, there is no simple formula to calculate p-value. But for Chatterjee correlations, just a very simple z-test. Okay? So that's why it has attracted a lot of attention over the past 2 or 3 years. And let's look at the basic definition for this new metric. Again, we have 2 continuous variables, x, y, and ID samples. And here we assume x and y have no ties. Here it's okay to have ties, but the formula can be a little bit complicated. But here, for the purpose of illustration, we consider the case that there's no ties. And the data is first arranged in terms of x. So here, x1 stands for the minimum of x, and xn stands for the maximum of x. And the y is not ordered. Y is just accompanied with x, and it's called the concomitance. And then we use Ri to denote the rank of yi, because x is already sorted. And this is pretty much like the time series. You sort the time points, and then you connect all the values of y. And then you look at the change of y. That's pretty much like a time series. And the definition for the Chatterjee correlation, here I use cosine n xy to denote the correlation matrix, the sample base, is equal to this form. And you can see this is a very simple form based on only the ranks of the y-axis. And Ri plus 1 minus Ri is kind of the difference in rank between each adjacent pair of y values. And then we use some coefficient to make the coefficient between 0 and 1. And here, let me give you some interpretation about why we use some specific value like a 3 here and n squared minus 1. And first, I think you can imagine it's a uniform distribution between 0 and 1. And if you randomly drop 2 points on the uniform between 0 and 1, the expectation of the distance between the 2 points is actually 1/3. And for discrete case, it's very similar. If you randomly pick 2 points from 1, 2, 3, 4, to n integers, the average, the expected value for the distance is equal to n plus 1 divided by 3. And also here you can see we have a totally n minus 1 terms. And you can see here for the expectation on the top, it should be 3 times n minus 1 times n plus 1 divided by 3, which is simply n squared minus 1, which means under independence, this correlation should be close to 0. And for dependence, and here let's consider y is just a smooth function or continuous function of x. And if y is a continuous function of x, we can expect the neighboring point, kind of a nearest neighbor, Ri plus 1 and Ri should be close enough. For example, it's equal to 1. And if Ri plus 1 and Ri are close enough, this term should be in the lower order than n squared. For example, just in the order of n. And that means if you have a large sample size, this quantity should be close to 1. And this will give you some metric between 0 and 1. Okay, so that's why here we have some specific numbers like a 3 and n squared minus 1. And this is some illustration about how versatile the Chatterjee correlation is. And here the first scenario is just a linear, and the increase the level of noise. For example, this one is 0 noise, and then increase the noise level. And here for linear, you can see the cosine n is close to 1. But this is not impressive because for many others, like Pearson's correlation or Spearman's correlation, is also close to 1 for this case. But if you look at the second and the third case, the second is a quadratic, and the third one is non-monotonic, so-called sinusoid. And even for this kind of complicated relations, the cosine n also gave very large correlation metric compared to the others. For example, for the quadratic pattern, the cosine n is 0.94, pretty close to 1. And for the sinusoid, either sine or cosine, the cosine n is still close to 0.9. And I believe if you use any other consistent test, for example, the distance correlation, for the first one, it might be large, like close to 1. But for the second and the third one, normally it should be below 0.5. So cosine n is very different from the others, like a distance correlation. Okay, because if you look at the definition, it's based on the local curvature, the local change, instead of a global change. Let's also look at some asymptotic result for this new metric. So here in 2021, the author showed that the cosine n, the sample-based quantity, actually converged to a population quantity defined in this way. This is so-called the DSS dependence measure. The DSS dependence measure is not new. It has been there for 10 years. I think first published in 2012 or 2013. But strategy correlation is, it's a new estimate. It's a consistent estimate for this metric. And also for both the population quantity cosine and sample-based quantity cosine n, they are both asymmetric, which means the cosine xy is in general not equal to cosine yx. Yeah, this is kind of a limitation of the this metric. For example, if you do the if you do the correlation study for the gene-to-gene interaction or protein-protein interaction, we don't want to specify which one is y, which one is x, right? We want to get some symmetric measurement. And here, a simple method to symmetrize is either by the maximum or by the average. And here we just use the maximum. I believe if you use the maximum, the power can be better than the average. And I will show you some result and some paper published last year. And the second, for the population quantity cosine, we can show is between 0 and 1. And 0 if and only if the two variables are independent. And 1 if and only if y is a measurable function of x, not just a continuous, as long as it's measurable, it's fine. But here I should mention the cosine n can be negative. So the cosine, the population quantity is strictly between 0 and 1, but the sample estimate can be negative. And this actually can be seen from the next theorem. The author also established the asymptotic normality of the cosine n under independence. Precisely, the square root of n times the cosine n will converge in distribution to a normal distribution with mean 0 and variance 2/5. 0 is because under independence, that's the null distribution. And the number 2/5 is from the so-called permutation oscillation. There's some theory behind that. And here you can see the cosine n can be negative because the center is equal to 0 and normal can be negative. Okay. And here we have two open questions by Chatterjee in his original paper, original proposal. Okay. Let me just read what he wrote. The first open question is, I don't have asymptotic theory for cosine n when x and y are dependent, because the 0 2/5 is only the null distribution, is under independence. For dependence, there is no asymptotic theory. Simulation result shows that even under dependence, this is also asymptotic normal. So the question is, what is the asymptotic behavior, especially whether it's normal under dependence? That's the first question. And this question is pretty hard. Second question is, one may also ask about the asymptotic null distribution of the symmetrized statistics, which is the maximum of cosine xy and cosine yx. It's likely that under independence, this behaves like the maximum of a pair of correlated normal random variables. At this time, I don't have a proof of this claim, nor a conjecture about the parameters of this distribution. Of course, it's easy to carry out a permutation test for independence using the symmetrized statistics. Okay. And the second question is, turns out, to be more straightforward, and actually I solved the second one. And interestingly, last year, both questions has been solved. Li and Han 2022 proved that under dependence, this is asymptotic normal, as long as y is not a measurable function of x, where sigma square is bounded by 36. And here the variance is not constant. It depends on what distributions you have, but it's always bounded by 36. And they use like masterful mathematical techniques to prove this. And for the second conjecture is about the Zhang distribution of the the cosine xy and cosine yx. Last year I solved this problem. And the independence, I show they are asymptotic Zhang normal. And also I gave the expression for the covariance between the two counterparts. And we show that the covariance is in the order of 1/n. That means when sample size goes too large, the covariance will vanish.
Question?
Yes.
What do you mean when you say under dependence and under independence? Are you talking about the observations or?
Yeah, so under independence means the X and the Y are independent. The two variables are independent. It's just like under the null hypothesis. Yeah.
And you are dealing with a sample.
Yes.
And you're also assuming that the sample is IID.
Yes.
Okay.
Under the independence between X, Y, and under ID samples, we have the result.
Okay.
So it's a non-distribution, right?
Yes, that's the null distribution, exactly.
Yeah, non-distribution, yes.
Because if you look at the questions by Chatterjee, he only asked what is the Zhang behavior under independence. See here, under independence. The first question is about dependence, under dependence when X, Y are dependent. But second question is only under independence. That's why here the second question is easier than the first one.
Mm-hmm. And so your result, okay.
Yeah.
So if they solve the first question, I think it's also possible to get the result for the second one for under dependence, right?
Yes, I think at
it's
least
possible.
Yeah, I think there's a possible way to go for the second one under dependence. Yes, you are right.
And you can have the power. So the dependence, you may have different dependence.
Right.
Yeah, so probably the first one, you need have some specification on the dependence, and otherwise probably too hard. I don't know.
Right, but their proof is very general. It can be any kind of dependence.
Okay, that's great. That's great.
Yeah, but the issue is that the variance is not constant. The variance only bounded by 36. For these different dependence patterns, the variance can be different.
Oh, okay.
Yeah.
But you can use, does they give the formula so that you can estimate this variance? Okay.
They do have a very complicated formulas for the sigma square based on very complicated integrations. Let me quickly show you some lemmas about the second conjecture or the second open question. So here we have the expression for the covariance between the two counterparts, and you can see it's actually essentially this is a very complicated fraction of two polynomials, and the order here is 1/n, and the next slides show you the visualization of this covariance. So here n is actually at least 4 because in the expression for C there's an n minus 3. So here n should be at least 4. We need at least 4 samples, and then you can see the the behavior of the covariance between the two counterparts. As n increase, it will decrease to 0. And I use both theoretical formula and also the Monte Carlo simulations. You can see it's pretty good fit. And here it's kind of non-monotonic at the beginning. This is n equals 4, and the peak is at n is equal to 6. I don't have any interpretation about why the maximum appears n is equal to 6, but both the simulation and the theory show that when you have 6 samples, the covariance is maximized. But the order here can be shown is big O of 1/n. So that means when you have a lot of samples, we don't have to worry about the correlations between covariance. And plus, we show the joint normality of these two counterparts. So that means if you take the maximum, the symmetries will follow a skewed normal distribution. You can also use the analytical calculation for the p-values. For example, if you do the correlation test for gene-to-gene interaction or protein-to-protein interaction, you can just use the symmetries, the Chatterjee test. You don't have to define which one is Y, which one is X. And so late last year, the author read a survey article focusing on this new metric, and he also discussed some advances, progress of this new metric, and also he asked some new questions. For example, what is the mathematical reason that this new metric is more powerful to detect non-monotonic, like oscillating patterns? And he also, in the survey article, he also confirmed that the two open questions in his original proposal has been solved last year. And some other extensions and discussions on this new metric. So this is still very hot topic, and I can see new papers coming out maybe every 2 or 3 weeks. For example, Audi et al. Studied the asymptotic power under local alternative, and also Azaki and Chatterjee develop some extension of this new metric to study the conditional dependence between 3 variables, and also it can be between 3 random vectors using the notion of nearest neighbor, and also some application to the manifold data and many other related literatures. And here, let's look at some performance about this new metric. As an empirical finding, this new correlation is powerful in detecting non-monotonic association, especially those with oscillating patterns. And the seemingly only disadvantage is that it's not so good at detecting the monotone and the smoother alternative, for example, linear. And this is some simulation done by the author. Okay? So if you have a linear correlation and increase the noise level, just like a linear regression, you increase the variance of epsilon. And you can see at the beginning, when the noise is pretty low, all the method did a good job. But when you increase the noise level, if you look at the distance correlation, is still powerful. There's some kind of a buffer. But if you look at the quasi n, is quickly drop down to very low power. So this is kind of the disadvantage of this new correlation metric, and we want to solve this problem partially. So to boost the overall power of this new correlation, we propose to combine with Spearman's correlation because Spearman's correlation is also rank-based, but is sensitive to the monotonic association. So basically, we want a new metric kind of with 2 wings. One is the Spearman correlation that's particular for the monotonic association. The other is a Chatterjee, which is for the non-monotonic association. Okay. And that way, the new test can be used as kind of an omnibus test. And here 2 questions arise. The question 1 is, what is the asymptotic joint distribution of these 2 correlations under independence? Hopefully, it's joint normal, and we can use the either a normal distribution or the skew normal. Okay. And the second question is, how much can they differ as a measure of dependence? If for any or for most of the scenarios they are very similar, there's no need to combine them. Okay, so we want to see some extreme case where one is very different from the other. For example, for some scenarios, you can show the Spearman's correlation can be very small, but Chatterjee's correlation is close to 1, and vice versa. And that's the motivation for the second part. We want to study the relationships between the 2 correlation metric. And this is the Spearman's correlation definition. You can see it's a very simple definition. Also depends on the ranks. And here I is because in the data X is already sorted, just I, and Ri has the same definition in the Chatterjee. So Ri is the rank for the Yi. And then you can show the expectation is under independence. Expectation is equal to 0. Variance is n divided by n-1, and is asymptotic. It will follow the standard normal distribution as n goes to infinity. Yeah, very similar to the Chatterjee correlation. And first, we want to study the covariance. Before we study the independence or joint asymptotic independence, we want to look at under finite samples, what is the correlation or what is the covariance. And here we have a lemma. If X and Y are independent, we show the covariance between sample-based Chatterjee and sample-based Spearman is equal to 0. And this is true for any sample size. It can be, for example, n is 5 or n is 10. The covariance is always equal to 0. And there's some details in the proof. And this tells us that for any sample size, there's no linear correlation. So if one increase, the other one may increase or decrease. Okay. But here we also mentioned that lemma 1 only indicates the uncorrelatedness is not the independence. Okay, because we know uncorrelatedness does not implicate the independence. Okay, and actually we can show in general these two correlations are dependent. I don't want to show they are dependent, but I just gave an example. When n is equal to 3, I can show the covariance between absolute value of the Spearman and the Chatterjee is equal to 1/24. So this indicates that they are dependent. If they are independent, then for any transformation, the covariance should be 0. Okay. So that means in general, they are dependent, but uncorrelated. And the key lemma for this work is lemma 2. So when x and y are independent, we show these two are asymptotic joint normal. And some key steps include the coupling method by Angus, central limit theorem for the M-dependent sequence, and Kramer-Wald device. If you're interested in the proof, you can take a look at the preprint. And also combine the lemma 1, lemma 2, we can show these two are asymptotic joint normal, and the mean vector is 0, and variance is 1 and 2/5. So we can use this result to combine these two tests into a new one, and the new one will have a analytical p-values. And this is some illustration about as n goes to large, these two are more like joint normal. Okay, so here I change the sample size from 10, 30 to 100, 500. You can see here the x-axis is the Chatterjee and the y-axis is the Spearman. As n goes to large, you can see the joint behavior is more like more and more like the joint normal. But when n is small, it's like a V shape because the Spearman is can be negative. It's between -1 and 1, but the Chatterjee is mostly between 0 and 1. So that's why here at the beginning we have some V shape. But as n increase, for example, n is equal to 100, there becomes a joint normal. And now the second question: how much can the two correlations differ as a metric of dependence? So first, we want to find some special case where Spearman is pretty small, but the Chatterjee is large. And this one is very, very easy to construct. You can just think about the absolute value. Y is equal to the absolute value of x, like the V shape. And here is some special case. Actually, I showed that for any epsilon which is positive, there exists the ranks such that the absolute Spearman is below epsilon, but Chatterjee is larger than 1 minus epsilon. And you can just use the special case here. This one is pretty straightforward because the Spearman can be only used to detect the monotonic. The second one is not that straightforward. In the second special case, I want to find, for example, given that the Chatterjee is very small, I want a large Spearman, but that one turns out to be more complicated. And mathematically, this can be formalized as this optimization problem. So given this constraint, which means given Chatterjee is below than some threshold epsilon, what is the maximum of the Spearman's correlation? And here the difficulty is that Chatterjee can be also detect a linear relation. So if Chatterjee is not small, then it should be some, when the Spearman is not small, there should be some linear relation or monotonic relation, and Chatterjee is also not small. But here I find a way around it. Okay, so I construct a special case where overall it's monotonic, but there's a lot of local fluctuations. Okay, you can see the the detailed setup. And for this special case, I show that for any epsilon which is positive, we can find the ranks such that the Chatterjee is pretty small. It's just equal to the epsilon plus some minor term, but the Spearman is equal to 1 minus this term. And at the examples, when n is equal to 100, we can find the ranks such that the Chatterjee is as low as 0.06, and the Spearman can be as high as 0.75. And the second one is Chatterjee is 0.13, and the Spearman is about 0.8. So this means that under some extreme scenarios, these two correlations can be very, very different. So that's why we have motivation to combine these two. The last part is about the combined or the kind of integrated test. The IN stands for the integrated test. It's a maximum of the absolute Spearman correlation because the Chatterjee is mostly positive. So we want to take the absolute value for the Spearman. And then we can show the analytical p-value is equal to this simple quantity. The phi here stands for the standard normal CDF. And you can just use the p-norm function to calculate the p-value. And we also established the consistency of this combined test. The proof is in my paper. Questions?
I was just thinking, well, would it not be maybe simpler to consider a combination of these two instead of maximum?
So the combination here simply means, when the correlation is linear, mostly will go to the Spearman. And if the correlation is non-monotonic, non-linear, mostly will go to the Chatterjee.
Yeah, but then if you put if instead of defining it like this, you have a weighted average of the two, or simply an average of the two, or maybe some maybe squares, you would still have the same conclusion as far as the dependence is concerned, right?
That's a very good question. So here I just take the maximum, but as I mentioned, we can also do any kind of a combination. You can do average, weighted average, like a weighted square maybe. But I think at least I compare the maximum with the simple average, and the maximum looks like more powerful.
Oh,
yeah. I think in the future it might be interesting to explore what is the the kind of the best combination. Yeah. There could be some better strategy to combine these two tests. Yeah. And also because these two correlation metrics are asymptotic joint normal. So for any combination, the p-value should be easy to calculate.
Yeah.
For example, if you take the average, it's also normal.
Yep, that's the thing. That's why I pointed to that. Maybe it could be an easier way to.
Yes. Yeah. That's a good direction. Some simulation studies. For the first simulation, we compare the power, for the three tests and also some competitors. Sn is the Spearman, and the Kozai is the Chatterjee, and the In is the integration. And we consider four alternatives. We consider linear, quadratic, sinusoid, and stepwise. And we consider 5 sample size from 20, 40 to 100. So 20 can be considered as the very small sample size in this case. And also we can see the how I set up this simulation. So X is from uniform, and Y is some regression of X, and here epsilon is from the normal distribution. So here we have a linear and quadratic, sinusoid, and stepwise. And here for the stepwise, I just use the monotonic. It's a 1, 2, 3, and 4. We can also try the non-monotonic. And this is the part of the result. So here you can see the solid line is the integrated test, and the dotted line is a Spearman, and the dashed line is the Chatterjee. Okay, so for linear, we can see the Spearman is the most powerful one, but the integrated test is also good. And for quadratic, you can see the Spearman totally failed, is off, and the sinusoid is also off for Spearman. And for the stepwise, because it's monotonic, you can see the Spearman is also the best, and Chatterjee is the worst. Okay, but here you can see that for the integrated test, it's never the winner, but it's always close enough to the winner. So that's exactly what we want. For any kind of dependence patterns, if you use the integrated test, it's not the best, but always close to the best scenario, best case. Yeah. And especially when the data set contain a mix of both monotonic and non-monotonic dependence patterns, I believe the integrated test should be more powerful. You can use that to get more positives. And also we compare with some existing method. In addition to the Chatterjee and the Spearman, we also compare with the symmetrized Chatterjee, which is the 2022 paper. Hofstee is also popular, and the BKR is also a popular measurement, and the proximal deciles is the sign covariance. So all these are kind of a consistent test. And also you can see the integrated test did a good job for all the scenarios. For linear, it's close to the winner, and the quadratic is also, I think, ranked second or third. And for the sinusoid is also close to the second best one. And for the stepwise is also in the best group. Yeah. So for the linear or sinusoid or stepwise, you can see a big separation between two groups of a test. And the new test, the integrated test, is always in the better group. Okay. If you look at the solid line, to a linear is here, and sinusoid is also here, and stepwise is also here.
Just one quick question. You're talking about empirical power. What are the alternatives of the test that you're doing? Sorry if I missed that.
Sure. Alternative is just a linear, quadratic, sinusoid, and stepwise. So under each alternative hypothesis, we look at the power. So the 4 alternatives simply means 4 different correlation patterns. And we want to look at what is the performance of different tests under different correlation patterns.
Yeah. So
what are we assuming that in one case there is no correlation, and against there is that kind of correlation, or what? That's what I want to know. What are the alternatives of the test?
So here, for example, for the linear, the underlying a pattern is y is equal to x, right? And then we can just generate random samples and then use different method to look at the power. We just use the p-value, whether the p-value is less than 0.05.
My question is the power of what test? What are the alternatives of the test that you are getting to do the power? Maybe I'm misunderstanding something.
Alternative, it is a linear. It is a linear y equal x plus epsilon, and H0 it's x and y are independent. Right now, they consider the power.
That's what I want you to know. What are the alternatives of the test?
Your mind is out of.
Yeah. So. Okay.
Actually, for the new test, the p-value is just calculated from the asymptotic, the analytical p-value formula. Yeah. Okay. So first you calculate the IN and then use the z-test, kind of the z-test.
Oh, that's fine. I just wanted to understand what the pictures were showing. So
okay.
You are seeing how often you will be wrong under each of the scenarios.
Yes.
For independence.
Yes, just like the true positive rate, the TPR. Yeah.
Okay, thank you.
So Zhang have another question.
Yeah.
So this simulation study, you assume X has a uniform duration from from -1 to 1. It's bounded, right? So how about if X is normal also, for example, unbounded?
Yeah, that's a good question. So for all my simulation, I just use X from uniform. I can also try the normal distribution, for example, it's unbounded.
Okay, all right.
Yeah, because it's a kind of a rank based. But it could be, could be a little bit different. When X is unbounded, there could be some different performance for some tests.
Oh, X is not symmetric. So here X is bounded and symmetric.
Right.
If X is not symmetric, I don't know. Yeah. No.
Yeah.
All right.
Okay. Thank you for the question. So in the second study, we look at the p-value bias. Because we use the analytical p-value, we use the asymptotic p-value. And here you can see the comparison between the exact p-value, which is from the permutation. And then the y-axis is the asymptotic p-value. And you can see here is a good, a good fit, good lineup between the two p-values, which means, for this simulation study, the asymptotic p-value is pretty close to the exact p-value. And also we summarize the p-value bias. The p-value bias is defined as the asymptotic p-value minus the exact p-value, and you can see some kind of inflation for the p-value, or kind of a conservativeness of the p-value, especially when sample size is small. When you have only 20 samples, the p-value is slightly larger than the true p-value. So this indicates that when you have a small sample, your test by the integrated correlation might be slightly conservative. But when sample size increase, this bias will vanish. And some real data, and this is also the data set used by the author, is in the R package, Minerva. Okay. So here, originally we have an expression level of more than 6,000 yeast genes over 23 successive time points during the cell cycle. And the process data set has 4,381 genes, which is available in the package. And then we want to compare the Spearman, Chatterjee, and also the integrated test. And for all the three tests, we use the asymptotic p-value adjusted by the Benjamin-Hochberg procedure to control the FDR at 5%. And this is a summary about how many significant genes identified by 3 method. And by Spearman, we harvest 385, and by Chatterjee, we got 619. But by the new test, for the integrated test, we get 734, which means in this data set, basically, most likely it's a mix of both monotonic and non-monotonic association. And we show some examples. This is a random sample of 4 genes selected by the new test, but missed by the Spearman's test. And you can see all the 4 genes have oscillating patterns. Okay, that's why the Spearman's test will miss them. And the integrated test has the Chatterjee's component, so it can detect this kind of non-monotonic association. That's one example. The second example is some genes selected by the new test, but missed by the Chatterjee's test. So here you can see the all the 4 genes are kind of overall monotonic and smooth, but there's a big big noise. Okay? It's a pretty noisy data. And that's why here Chatterjee is based on the local change or local curvature. That's why here Chatterjee is not powerful for this kind of data. So overall, it's monotonic and smooth, but locally it's very noisy. So Chatterjee will fail, for this kind of gene expression levels. And some possible extensions. The first extension is the IN is generally also asymmetric, just like the Chatterjee. And when a symmetric measure is more suitable, we can consider this a modification, just like my 2022 paper. So we can combine into a maximum. This is the absolute Spearman, and then the Chatterjee from X to Y and the Chatterjee from Y to X. But here we don't have the joint asymptotic normality. Okay. So in my 2022 paper, we show the joint normality between the second and the last term. And 2023 paper show the normality between the first and the second, or the first and the third. But we don't have the joint normality for all the 3 terms. Okay. So the question is, how can we prove the asymptotic normality for these 3 different components? That's a difficult question for me. And the second one is, you can see the p-value bias. When the sample size is small, there's some positive bias, which makes your test a little bit conservative. So how to do the asymptotic expansion for the p-value bias reduction? For example, we may consider the Edgeworth expansion or so-called the saddle point approximation by incorporating some higher order moments, such as the skewness for the 3rd moment and the kurtosis for the 4th moment. Okay. And these 2 can be some interesting exploration for the for this new topic. And these are the 2 papers for this talk. The first one is about the symmetries, the distribution, and then the second one is just this talk. I just submitted the minor revision, and normally I think it should appear late this year or early next year. But there's a preprint, you can download and read if you're interested in that. Okay, I think that's all I have. Any questions?
Thank you.
Thank you.
Yeah,
I have one question about the p-value. You have compared all of the asymptotic p-value, and that's 3 to 9. The p-value later. That's that plot. Yeah, this one. Mm-hmm. So you're using exactly the p-value you obtained by the permutation, right?
Yes, I think I did 50,000 permutation to calculate the p-value.
And in my understanding, because I have some simulation from my work about the